problem 14.
Hello everyone, I hope you're doing well. In this video, we are going to solve problem 14 from chapter 12 of Material Science and Engineering by Kittel. Let's see the problem statement and we'll dive directly into the solution. The statement says that iron oxide, this is iron oxide molecular formula, has the rock salt crystal structure. It has a rock salt crystal structure and a density of 5.70 grams per centimeter cube. So we are given with the density. Now let's see what we need to calculate. This is the system that we are given with: rock salt structure like NaCl and density, which is this, and it's ferrous oxide. In part A, we need to determine the unit cell edge length, which is actually A, the lattice parameter. We need to calculate the lattice parameter. And in part B, we have to see that how does this result compare with the edge length as determined from the radii in table 12.3, assuming that the ferrous and oxygen ions just touch each other along the edges. So we'll find out we'll see how we can do that. Okay, we'll see how we can do that. Let's quickly get started with the solution. Let's determine the unit cell edge length from this information first. Solution. The problem is really simple. We know that the density is given by rho equals n primes n prime, atomic mass of first ion, which is ferrous, Fe+2, plus atomic mass of oxygen ion, because there are two different kinds of atoms, so we'll have a sum of both of these atomic masses, divided by Avogadro's number, multiplied by the volume of the unit cell. Well, this is the formula so far. Now, since we need to find out the lattice parameter, we can put the value of V in here. We know that V equals A cube. So let's put this value into this expression. It's rho equals n prime into atomic mass of ferrous plus atomic mass of oxygen ion divided by Avogadro's number into A cube. Now we need to calculate A. So let's take this thing into this side and taking rho here. So A cube here, and density will be divided onto the other side since it was multiplied. It is multiplying here, it will be divided here. It's rho here. Now it's A cube. We can take cube root on both sides. N prime A ferrous plus 2 plus A oxygen divided by Na into rho, and we'll take 1/3 power at the end when we'll have all of these things. So this is the formula that we'll be using. All right, now what these values are equal to, let's write all of them here. Na is the Avogadro's number. It is 6.023 multiplied 10 to the power 23. All right, next is density. Density is already given in the question, which was 5.70 grams per centimeter cube. We'll use it as it is. Then we have n prime. Since the structure resembles the rock salt structure, in rock salt structure we have 4 as the net number of atoms per unit cell. All right, all the structures that resembles the rock salt structures have n prime equals to 4, and their volume is also equals to A cube since the rock salt structure is cubic. Well, all right, then we have this thing, A ferrous, atomic mass of ferrous, that is equals to, it's 55.845 grams per mole. Then atomic mass of oxygen, which is 16 grams per mole. All right, so we know all of these quantities. Let's put these values into this expression and see what is the lattice parameter. So putting values into 2, A equals n prime is 4 into 55.845 plus 16 divided by Avogadro's number, which is 6.023 multiplied 10 to the power 23, and rho, which is density, it's 5.7. Okay, and the whole power is 1/3. Let's calculate this thing inside, and after calculating it, we'll take the cube root of it. Let's do this on calculator. This is what we got for the inside product. Okay, now I'm taking the cube root of it, and we can take it like there is another option to take the cube root, but I'm taking this one because it's available in most of the calculators. So it's 4.37 multiplied 10 to the power minus 8. The lattice parameter or the unit cell edge length is 4.374 multiplied 10 to the power minus 8, and it's in centimeter because the density was in centimeter cube. So the length that you are going to get is in centimeter as well. This is the unit cell edge length. You can convert them into angstrom or nanometer. It's totally up to you. We can convert it into nanometers. 4.374 multiplied 10 to the power minus 8. Centi is 10 to the power minus 2 meter. And it makes 10 to the power minus 10 meter. And 1 angstrom is equals to 10 to the power minus 10 meter. Unit is also included. So we'll write A to be equals to 4.37. Okay, 37 is fine. Angstrom. You don't need to write meter with angstrom because angstrom is a prefix with unit in it. Okay, and that is the unit cell edge length for ferrous oxide rock salt crystal structure. This is the answer number A. This is not included. And let's see how we can do the part B and how we can have a comparison. For part B, they are telling you to estimate the lattice parameter from the radius of the ion. Okay, so we know that the lattice parameter in a rock salt crystal structure is given by 2 times radius of cation plus 2 times the radius of anion. Here cation is ferrous plus 2 times radius of oxygen ion. Anion is oxygen. Let's put the value. It's 2 times radius of ferrous. Okay, first we need to mention them. We have radius of ferrous ion, that is equals to 0.077 nanometer. Okay, and radius of oxygen ion, that is equals to 0.140 nanometer. We can put them in nanometers as well. The result will be in nanometer automatically. So A equals, we can put values into this expression. 2 times radius of ferrous ion, which is 2 times 0.077 plus 2 times 0.140. The answer will be in nanometer automatically. Let's see what it equals to. We got 0.434. It's 0.434 in nanometers. Okay, and it is in nanometer. We can convert them into angstrom so that we can have a good comparison, and we can convert it like that. We can write 10 to the power minus 9 meter. Now angstrom is for 10 to the power minus 10, so we can do that by multiplying 10 to the power minus 1 and also multiplying 10 to the power plus 1. Okay, we can combine these two powers together to form 10 to the power minus 10. Okay, and 10 to the power 1 meter as well. And 10 to the power minus 10 into meter is actually angstrom, so we'll write them together, and it's angstrom. We can write it like that. 10 to the power 1 is actually multiplying it with this quantity gives 4.34 angstrom. And this is the lattice parameter or the unit cell edge length considering the radiuses of the ions. Okay, and it's theoretically determined. And the one that we determined from the experimentally determined density was 4.37 angstrom. It's 4.34 angstrom. There is a slight difference. You can find out the percentage error really quick and easily. Let's do that as well so that we have a good say about how much they differ from each other. So we can find the percentage error between the two lattice parameters obtained in part A and B. B as follows. Percentage error. So we have the greater length first, which is 4.37 minus smaller length, which is 4.34, divided by, we always divide by the standard value, the one that is accurate, and the accurate one is actually the one which was calculated from this experimentally determined density. Knowing that, we calculated the lattice parameter, so that is the correct one, and it's 4.37 angstrom. 4.37. You don't need to put any units in them, but make sure that all of them are in similar units. They shouldn't be in different units. Like everything should be in angstrom, not like it's angstrom and it's nanometer. No, that's not applicable and not allowed. Let's see what this equals to. Okay, multiply by 100 because we are finding out the percentage error. This is the percentage error, which is 0.686. 0.686%. Okay, we can see that the error is less than 1%. Hence, a good agreement, a good theoretical agreement for the lattice parameter, for the lattice length or unit cell edge length, of ferrous oxide. Okay, this one was the theoretical estimate to the lattice parameter. We did it theoretically knowing the radius of the anions and cations, and the other one was the original one. Okay, so that is it for this video. I hope you got it, and we'll meet you in next video. Till then, take care and goodbye.